So we're going to do kind of a hyperspeed review of linear algebra and matrix calculus. This isn't going to be by any means a substitute for having taken a multivariate calculus class in advance, but hopefully this helps you review some of the concepts that we'll be using a lot in this class, especially when we get towards optimization. So why do we need linear algebra and matrix calculus for this course? Well, in general, we'll be in a case where we have training examples, and for each example we have a bunch of features, x1 up to xn, and a label for that example. Now, we could just define all of our objective functions and optimization based on thinking of these as scalars. Define some function over this and try to approximate the label. But often it's going to work better to do the following. First, we need to realize that generally we're going to have a whole training set. So this is going to be example 1, and we have examples all the way up to n. And by the way, we also have parameters of our model, theta 1, theta 2, theta 3, and so on. Okay, so we have all of these data values. We can consider this like a matrix. We can consider our labels like a vector and our parameters like a vector. And now our training looks more like we take a big matrix of training data, we take a vector of parameters, and we try to optimize that to approximate our labels. Now, often it's going to be much more efficient to do it this way because often we can optimize across our entire parameter vector simultaneously. That's going to generally be much faster than optimizing each parameter separately. Okay, so that's why linear algebra and multivariate calculus are going to be useful in this class. Often we have a situation like this. There's going to be more situations where these are going to be useful, but this I would say is the main one. So let's remind ourselves, what is a vector? A vector is just a list of n real values, x1 up to xn. And of course here being the number of real values. So generally we write this. Note that we're using a bold face for x to indicate that x is a vector, and non-bold face here indicating that x1 is a scalar. Scalar meaning a single value as opposed to a list of values. We'll write that x is a vector by writing that x, and here I mean boldface x, is a member of Rn. This R with the two lines here is the set of real numbers, so we're saying there's a set of real numbers to the n. A matrix is a set of m times n numbers arranged in a table. Again, we're using here bold notation, and we're using a capital letter. So we're using a bold capital letter to indicate a matrix. Note that in this course we also use capital letters to indicate random variables. So it can be a bit confusing, and we'll try to make it clear at the time whether by a capital letter here we mean a matrix or random variable, or perhaps a random variable that is matrix valued. Likewise, we write a in r to the m times n. Note that here we have m rows and n columns. We always write rows first. So that's why we have m times n versus the reverse. Sometimes it can be useful to think of matrices not as a table of numbers, but as a matrix being a list of column vectors. So this is the same thing here. Note that we have A1, A2, all the way up to AN. These are the different columns of A. So each one of these is a vector. Equivalently, we can consider a matrix as a list of row vectors. Again, note we have the same thing here where we have A1 colon indicating we want all of the columns for the 1th row. By the way, when we list a vector, we almost always mean a column vector. So if we want to indicate a row vector, we'll almost always transpose it. That is, define it as a column vector and then use the transpose when we see it on the page. Transpose, by the way, means to flip the rows and columns. What do we do with matrices and vectors? Well, one big thing we do is we multiply them. Okay, so if we multiply a row vector times a column vector, notice here we have x transpose. X is implicitly a column vector, so to turn it into a row vector, we have to transpose it. X transpose y is the sum over 1 to n, where n is the number of dimensions of x and y, of xi times yi. This is called a dot product. Also an inner product. Vice versa, what if we put a column vector times a row vector? This is a different kind of product called an outer product. This, by the way, a inner product is, notice that this is a sum here of products of scalars. So this thing is a scalar. That is, it's in R with no exponent. This thing here is a matrix of dimension m times n, which are the dimensions of x and y respectively. It's a matrix where the components are equal to the product of each of the elements of x and y respectively. So the top left is x1, y1, x1, y2, dot, 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 all the way up to x1, yn. Second row is x2, y1, and so on. Why do we define it this way? That is, with a row times a column, meaning something different than a column times a row. Well, it's to make it a special case of matrix multiplication. Okay, so what is matrix multiplication? That's the case where we multiply two matrices, A and B. Let's say A is a M by P, and B is a P by N. That will make C M by N. So note, for matrix multiplication, the number of columns of the first matrix has to equal the number of rows of the second matrix. And one consequence of that is, note that matrix multiplication is not commutative, meaning you can't swap the orders. If we did B by A, we would get something with n columns multiplied by something with m rows, and that wouldn't make any sense. Okay, so not commutative. What is this multiplication? C is defined as follows. The ijth entry of C, notice that this is not bold because this is a scalar now, because it's a specific value of C. The ijth entry of C equals the sum k equals 1 to, this is P here, my notation I think is slightly different than the book, of aik times bkj. So that defines matrix multiplication. I think that's not necessarily always the best way to think of it. Here's another way to think about matrix multiplication that I think is often more useful for one's intuition. It's the following. The Cijth entry, that's this guy here, is the dot product of the first row of A times the first column of B, and vice versa for all the other entries of C. There's some other ways to think about matrix multiplication. I think each one is useful in some different cases. I encourage you to go through the textbook and sort of mentally remind yourself of different good ways of thinking about matrix multiplication. There's an equivalent way which is based all on the outer product, which I think can help us with intuition some of the time. But more generally, this, from a mathematical perspective, this definition here uniquely defines matrix multiplication for us. Here's another property we're going to be using a lot in this course, is a matrix inverse. So if we have a matrix A, we write A minus 1 as the matrix inverse. For A minus 1 to exist, A must be square and invertible. Not all matrices exist, or not all matrices are invertible. That is, for some matrices, the inverse doesn't exist. That is, there doesn't exist a matrix that we can find that has this property. This is how we define the matrix inverse, such that A times A inverse equals the identity matrix. Recall that the identity matrix is the matrix with 1s on the diagonal and 0s elsewhere. So not all matrices A have an inverse. If the inverse does exist, we call it invertible. In each case where we're going to use the inverse, if we want to do it in a generalizable way, that is, make a method that we're sure is going to work in all cases, we have to somehow argue that the matrix inverse does exist. In the next slide, we're going to give one way to show that it exists, one property where if that property holds, then A will definitely be invertible. There are some more ways to prove that a matrix is invertible. It's that we're not gonna cover in this course. Well, in each case in this course where we look at the matrix inverse, we'll talk about what happens if the inverse doesn't exist, and that's something you should always keep in your mind. If you want to use an inverse, you first have to ask, okay, but what if it doesn't? What if it's not invertible? It's very similar to dividing scalars. Anytime you do division, you have to have something in your back of your mind that says, oh wait, but what if this number is 0? What happens in that case? Because of course you can't divide by 0. Let's look at a specific expression that we're going to see a lot in this course, like this: x transpose ax. This is called a quadratic form. It's in some ways analogous to x squared in scalar algebra. We're going to see this a lot. It's going to come up, for example, in a multivariate Gaussian. By the way, here A is a matrix and X is a vector. So we'll see why it comes up so much, but let's look at some properties of this quadratic form first. First thing, it's not too hard to convince yourself that even if A is not symmetric, you can come up with a matrix that is symmetric that has the same output of the quadratic form as A. That's in the textbook. It's not too hard to think about. And for that reason, we usually assume that a matrix that's in a quadratic form is symmetric. Okay, but we'll make sure to say that explicitly when we come up with it. A symmetric matrix, by the way, is one that's equal to its transpose. Okay, so we usually assume A is symmetric. By the way, this should be obvious, but A must be square. Why does it have to be square? Well, it's being multiplied with something that has n columns on one side and n rows on the other, because this is the same x, obviously. Okay, so A must be square and it must be symmetric. If it's the case that x transpose AX is greater than 0 for all x not equal to the 0 vector, this upside down A means for all, then we call A positive definite. So again, a matrix A is positive definite if and only if it's this case. If this is the case that x transpose AX is greater than 0 for all x not equal to the vector of all zeros. Of course, if x is equal to the vector of all zeros, this thing is always going to be 0. It's not hard to convince yourself of that. One nice property of positive definite matrices is that they are always invertible. So this is one way to prove that your matrix is invertible, is if you can show that x transpose AX for your particular matrix is always greater than 0, it will always be invertible. If it's the case that this is not necessarily greater than 0, but it's greater than or equal to 0, then we call it semi-definite. That was a review of linear algebra. We're going to talk about multivariate calculus, that is, derivatives of vector-valued functions in just a second. But first, let's remind ourselves what a derivative is. Derivative, which we write as f prime of x for some function f. So f is a function that takes in a scalar x, outputs a real value. F prime of x is its derivative. We also write it like this, df over dx is the following. Here's the formal definition. Informally, it's the slope of a function. So if we have some function like this is f of x on the vertical axis, x on the horizontal axis. F prime of x is the slope of the function. So let's draw f prime of x. I made life hard for myself here. It's going to be a large positive number here. It's going to be 0 here because it's flat. It's going to be a large negative number here. It's going to be 0 here again, 0 here, positive here. So the derivative is going to look something like that. Again, it's defined by this limit. The limit essentially means is asking, if we add a small value to x, how much does f change, and how does this change as h goes to 0? It's worth noting that not all functions have derivatives. In the case where a function is, for example, discontinuous, that the function won't have a derivative at that point. We're going to assume in most cases that the functions we're going to use do have. let's generalize the derivative to a multivariate function. So we're going to imagine that f here is a function that takes as input a set of variables, x1 up to xn, and outputs a scalar, y. So we might write f as being a mapping from Rn to R, because again, it takes as input a vector and outputs a scalar. We could look at cases more generally where it goes from a vector to a vector. That's not going to be too relevant in this course. The reason this particular setup is going to be very common is that very often it's the case that we're looking at a function which takes as input, for example, a set of parameters of a model and outputs its likelihood. And we're going to want to take the derivative of the likelihood and set that to 0. That's going to be by far the most common case where we see the multivariate derivative in this course, also called the gradient of the function. Okay, how do we take derivatives? Well, it's very simple. We can just take a partial derivative with respect to each value. That is, just ask, how does f change if you hold everything fixed except a particular value, xi? That gives you the partial derivative of f with respect to xi. Notice that we replace the d with this backwards delta sign. That's how we indicate that it's the partial derivative of a multivariate function. And then here, this is just a generalization of the derivative. Note that here we have the vector x, and here, instead of adding h to the single value, we add just to xi. One way to write that is h times, this is the unit vector ei, which has zeros except for at the ith row where it has a 1. You could also call this a one-hot vector. E for element vector, I think, is where the E comes from. Okay, so that's the multivariate derivative, the gradient. Same thing as the normal derivative, just for a single variable. The full gradient of a function we write like this. G here is a vector now, and it's the vector of partial derivatives. That is, so this g we call the gradient of this multivariate function f, as opposed to the individual partial derivatives. And that's just a vector of df with respect to x1 all the way up to df with respect to xn. That is just the vector of partial derivatives. There are a couple different ways of writing this. We can write it as g. We can write it as df over dx, where we use a vector here, or we can use this. This is the upside down delta, which we call nabla, the nabla sign of f. All different ways of writing the gradient, meaning the vector of partial derivatives. Let's look at gradients of some common functions that we're going to encounter a lot in this course. We're just going to look at super simple ones here. If we have a constant vector times x, and we want the gradient with respect to x, well, it's really simple. It's just that constant vector a. Note here that we define the gradient as the column vector of partial derivatives. So here, it's not, even though we had an A transpose here, A transpose is a row vector. Wouldn't make sense to put A transpose here. We have to think about it as the vector of partial derivatives. So what is the partial derivative with respect to x1, it's a1, partial derivative with respect to x2, it's a2, and we're going to arrange those in a column vector. That means we end up with A not transposed. Be worth thinking, what happens if we flip this, if we wrote derivative of x transpose A instead? I'll leave that as an exercise. Would we end up with A transpose or A not transpose here? Okay, let's do something slightly more complicated. What if we have B transpose AX? Again, B is a constant vector, A is a constant matrix, X is the thing we want the derivative with respect to, which we're showing because we have it in the denominator here. Well, notice that B transpose A, that's still just a vector, so it's really just, it reduces to this case here, but notice again that we have to transpose it to get a column vector out. One more. What about the quadratic form that we just saw on the previous slide? X transpose A times X. Again, A is a constant matrix. X is the thing we want the derivative with respect to. You can convince yourself that it's the following: A plus A transpose X. Again, if we have the quadratic form, often we'll be assuming that A is symmetric. So A plus A transpose, if A is symmetric, these two things are the same thing. So it's just 2AX, or equivalently 2A transpose X. Again, asymmetric, so taking its transpose doesn't matter. Okay, you could have proved all these from first principles just using the limit definition, or by taking the taking each partial derivative separately and using your knowledge of scalar derivatives to form that vector and see what it is. But if you want to skip some steps, at least in these simple cases, you can use these that we sort of pre-computed for you. What about the second derivative of a multivariate function? We're not going to use this too often, but we are going to see it a couple times. The second derivative is written like this: nabla squared of x, also like this, d squared f over dx squared. This is called the Hessian, after a mathematician, I believe. And the second derivative is a matrix. It's the following matrix. The diagonal entries are the second partial derivative of the function with respect to each variable. So second derivative of f with respect to x1. Same thing across the whole diagonal. So the bottom right entry is second derivative of f with respect to xn. The off-diagonal entries are the following: the derivative of f with respect to x1, and then the derivative of that with respect to xn. So it's the second derivative with respect to two different variables. A way to get that is just to first find the partial derivative with respect to x1, and then take the derivative with respect to xn. Turns out it doesn't matter if you switch the order. We're not going to prove that, but it turns out to be true. First take the derivative with respect to xn, then take the derivative with respect to x1. That's how you get your off-diagonal entries. Okay, that's it for our super quick review of linear algebra and multivariate calculus. As I said, hopefully that was a review for you, but hopefully it kind of jogged your memory and helped you remember some of these topics that we're going to apply very often in this course. We're going to apply especially when we get to optimization. For optimization, the way we're going to be doing optimization is almost always by taking the derivative with respect to our function, sometimes the second derivative, and usually we're going to be doing that with respect to all of our parameters at the same time, meaning we're going to be doing multivariate derivatives.